Well, hello everyone. Good afternoon and welcome to today's webinar on the Mauve Science program, and thank you for joining us. My name is Richard Archer. I'm part of the Blue Sky Space Team. I'm based in our London, United Kingdom office, and I'll be hosting today's session, which is expected to last around an hour. So this is actually the second in a series of Mauve webinars, which we're planning for 2026. And each one we've decided to discuss different aspects of the science program, which is a UV mission to study stars. So similar to the webinar we ran in February, we're going to focus on introducing the science goals and opportunities for the first year of the program. And to bring the session to life, I'm delighted that we're joined by two members of the Mauve Science Team who are going to present their science themes that they are personally involved in. In the top left, we have Christopher Johns Krull. He's a professor in the Department of Physics and Astronomy at Rice University. Since 2022, he's also served as the chair of the department, and his primary areas of research are observational studies of star and planet formation. Top right is Dr. Chuanfei Dong. He's an assistant professor of astronomy at Boston University and a member of the Institute for Advanced Study in Princeton. Some of Chuanfei's research interests include star-terrestrial planet interactions, very applicable for Mauve, and magnetic reconnection and turbulence. I'm also going to be helped by some of my Blue Sky Space colleagues. Marcel Tasseni is one of the co-founders. Benjamin Wilcock is the senior program manager, and his job and his team is to execute the three-year science program for our members. And Ariana Saba is responsible for the all-important science operations. So the agenda today, as I said, 50 to 60 minutes, depending on how fast and how many questions we have. Like last time, we'll do a quick introduction to Blue Sky Space. Marcel will do that. I'll do a brief introduction to Mauve, and then we'll move on to our science theme talks. Chuanfei will go first, and then Chris. Then we will hand over to Ariana, who's going to talk about first light and the commissioning activities for the satellite. Then Ben will talk about the science program, how we're delivering that for the first year. And then I'll close with some remarks on participation, and then we'll open up the floor for questions and answers. Please post your questions in the Q&A box on Zoom. We are using the Zoom webinar format, so it's a little different than you're probably used to, but you can see the Q&A box highlighted there. Parul's going to be monitoring that, and at certain points within the webinar, we'll stop and we can take questions. We will also be recording today's webinar, and I will send that to everyone at the end of the webinar. So on that note, I'll hand over to Marcel, who will do an introduction to Blue Sky Space.
Thank you, Richard, and thank you all for participating in today's session. So as Richard mentioned, I'm one of the co-founders of Blue Sky Space. The three of us co-founders come from an academic background, working at UCL on a number of different projects. And we started Blue Sky Space because we felt that there was an opportunity to accelerate the provision of scientific data sets collected from space. I'm sure many of you are familiar with the current ecosystem of space missions with the big space agencies. And in the context of a very rapidly changing space industrial sector, we wanted to try a different approach to delivering data sets directly to the universities internationally. So Blue Sky Space very much focuses on small satellites. At the moment, we're working on a low Earth orbit set of satellites, and only for doing science cases for which there needs to be enough demand to justify the construction of a particular satellite. We are not in the business of trying to do a James Webb-like satellite or HWO class satellite, where we think that's perfect for the agencies. We're really talking about satellites that can be done in a reasonably affordable way, in a reasonably rapid time frame in a low Earth orbit. Next slide, please. The approach that we're doing is we work with the industry across the world who builds these satellites regularly for a whole series of applications. So we work with specific platform manufacturers to pick the most appropriate off-the-shelf platform solution available, plus with institutions internationally and companies internationally to pick the right payload solution for the satellite. So the key point here is that we don't build the satellites ourselves. We're, of course, heavily involved in the interface between science requirements and technical specifications. And in particular, when it comes to the software, when it comes to the planning and the downloading of the data and the management of the data on the ground, we're heavily involved in that. But the hardware is really left with the suppliers who know their experience. And what we do is we focus on components which are as high heritage as possible. So we reuse existing solutions which have been flown before, high TRL applications, or when appropriate, analogous technological solutions which can be used in the low Earth orbit to deliver what we need in a very efficient manner. So the approach that we're working on is try to deliver these satellites as quickly as possible, typically under 3 years. And we've got a roadmap of different projects, as you can see on this slide. Mauve, that is, of course, the focus of this presentation, has been in orbit now for a few months. We've got the Twinkle space mission, the project with which we actually started Blue Sky Space, which is a larger spacecraft focusing on exoplanet spectroscopy, going from the visible to the near infrared. And then we've got a roadmap with other satellites, Mauve Plus, so larger class of satellites doing UV as well. And then beyond that, we've got perhaps our most ambitious program out there, Radio Luna. That's where we depart a little bit from a low Earth orbit. That's a fleet of CubeSats to fly in the orbit of the moon to do radio astronomy from the quiet side of the moon. Now, that's a paper study at the moment, and we're working with the Italian Space Agency on this. That's very much for the future. But it's just to indicate the approach we're taking. We are getting more and more questions from science communities about other opportunities for flight of either payloads and instruments which are already available or other science cases that could be explored with this model. And so we are very much looking for ideas from the community as well in terms of what we could look at as part of our roadmap of future satellites. Next slide, please. So we've put together a team to deliver this vision. We've got a combination of experience and history from academia, the space industry. We've got teams working in software, in science data analysis, and of course the management of the community and working with the scientists internationally. Next slide. And the final slide I've got is just a bit of context of how we operate as an organization. We are somewhat different to what the agencies are doing in terms of how they procure these satellites and how the data is made available. What we are doing is we're financing the satellites upfront. We take the commercial risk as an entity to finance the satellites, pay for the launch and their operations. And then what we do is we made the data sets available on a membership basis, perhaps in a similar way as some of the ground telescope networks operate, to cover the cost of operations and the scaling up of the organization and to go into the next generation of satellites as well. And we've secured funding from a series of different sources. We've secured, of course, funding from different grant programs, and nominally a lot related to industry partnerships as well, but also the universities who are participating in different science programs, and finally through investment from private individuals who are supportive of the kind of developments we are doing and want to see the growth of the space sector in the science domain as well. So I think that was my last slide, Richard.
Yeah, thank you, Marcel.
Thank you very much.
Okay, so before I hand over to Chuanfei to do the first talk, I'll do a whistle-stop tour of Mauve. So Mauve is a UV spectrophotometry satellite, so very much low-resolution spectroscopy, and its aim is to study stars. We're actually delivering Mauve as a 3-year science program, and any science can join as a member, and you can collaborate with other members from across the world. And the entire data set is shared and can be used by any member of the collaboration. The actual science isn't decided by Blue Sky Space, it's decided by the members, and it's planned on a year-by-year basis. And each year a science team is formed who work together to decide the science themes and ultimately design the observational program. And you can see here for year 1, we've allocated around 5,000 hours so far across 4 broad science areas, and Ben will cover those science areas later on in the presentation. So this number of hours really lends itself extremely nicely to things like long baseline observations of targets. So you can sit and stare at a star and capture an event like a stellar flare, or you could even do a population study using short snapshots of lots of targets. And we have both that are covered within the program and have been designed as part of the individual science themes. And of course, you can also revisit these targets over the course of either a year or years to see how they change over time. So studying the variability of the selected targets is really a key aspect, and I'd say a USP of the program. As Marcel said, that we are grateful that we were part funded by the European Commission. Our suppliers, C3S in Hungary, built the spacecraft, and ISIS Space were responsible for the ADCS. Just a quick run through on the satellite. So it's 20 kilograms. It's launched into a low Earth orbit, sun synchronous orbit. At the frontier, you have the telescope. It's a 13-centimeter telescope made by an organization in Italy called Medialario. And that's connected behind it to two spectrometers. One of them is redundant. Those spectrometers are provided by a Dutch company called Avantes. And Avantes inside the spectrometer are using a Hamamatsu detector, a CMOS linear array detector. And that gives a wavelength range of between 200 to 700 nanometers. And we capture that in a single shot. So it's near UV invisible. The resolving power is 20 to 65. So once again, low resolution, depending upon where you are in that wavelength range. So Mauve is very much suited in the program to bright targets. It's single target spectroscopy. We're not looking at a patch of sky. So we try to isolate a single target if possible within the field of view, which is 95 arc seconds full cone. And the great news is that on November the 28th, 2025, we launched Mauve. So that went on SpaceX Transporter 15. I think if you can see my cursor, it's down there at the bottom with this myriad of satellites on a rideshare. Successful launch, and Mauve was deployed 1 hour after the Transporter 15 arrived in orbit. So everything was successful as far as the launch is concerned. Okay, so I think it's time for the first of our talks. So Chuan Fei is going to talk about stellar CME detection and possible UV dimming signatures following flares. So Chuan Fei, if you'd like to share your slides, and over to you.
Hello, everyone. My name is Chuan Fei Dong. It's good to take some time off from Boston University. So I spent this semester at Institute of Advanced Study in Princeton. And today I'll be talking about stellar CMEs detection, possible UV dimming signature follow flares using Mauve telescope, together with Dr. Hongpeng Lu. So I will start with scientific motivation and significance. Then later I will talk about observational strategy and expected outcome. So the impact of the CME in our solar system, like on Earth, is already well known. And we know flare very well, but there's also a counterpart, like a magnetic bubble release from the star following flare. So this causes CME, coronal mass ejection, which are violet ejection of magnetized plasma from the sun and other stars. CMEs can be very volatile, and is also probably the largest eruption phenomena in our solar system, which can cause a lot of disturbance in our planet Earth and also on other planets like Mars, where people will live in the future probably. So it's very important, but so far the detection of the stellar CME on other stars is very limited and has not been well established if there's really stellar CME from other stars or not, at least based on the current observational limitation. And back to about 15 years ago, people used TESS telescope to find the flare, and you can see those sinusoidal variation on the stellar brightness is because of the rotation of the sunspot. But there are also those spike structure. These are the stellar flare. And the many sun-like stars produce super flare. Those flare energy is much higher than what we can observe in our current solar system because our sun is no longer that young, and also because it's a G-type star. So when a star is smaller, dimmer, or younger, in general, they are more active. And many stellar CMEs might be larger in scales, fast in speed, and occurring more frequently than solar CMEs. Yeah, other young star or M-type star. Yeah, and the stellar CME may be very important for exoplanetary space weather. These days, if you study astrobiology, stellar flare and the stellar CME is very hot topic because it can affect planetary atmospheric escape, and eventually can answer the question if there's life on other bodies or not. At least this is one of the main driver for atmospheric escape, especially the secondary atmospheric escape. So how we detect CME? There are different methods, but if we, if I propose to use the corona dimming as one of the possible signature to detect CME. So on the left, because when the CME erupted, it will release some material from the star. So the left panel is show both panels show you the dimming. So if we see pre-flare and after flare the signature become dimmer. So this is so-called coronal dimming, either from left panel or right panel. The left panel, people only integrated a very small region on the stellar surface. On the right panel, it's the integration based on the whole stellar surface, but both are the sun. So stellar CME are often accompanied by a sudden decrease in emission across UV, X-ray, and H-alpha. And H-alpha wavelength is covered by a Mauve telescope, which can manifest as either emission dimming or obscuration dimming. So there are two ways. The emission dimming is basically the material is lost from the stellar surface, so it's become colder. The hot material gets escaped, and the obscuration dimming is due to the erupting of the filaments material blocking the background emission. So the later, basically, like there's an umbrella, on top of the stellar surface, so you cannot observe those hot material below the umbrella. And such coronal dimming also has been observed on other stars, because we know when we observe other stars, there's no spatial resolution, so we have to integrate over basically we are integrating over the whole stellar surface. And some people have concern maybe it's the signature is not strong enough to see that, but at least from previous study we can see such dimming can be observed even on another star, so which indicates Mauve. It's possible Mauve can also observe such signature. Yeah, so this basically, if you see the red part, the later emission is weaker than the previous one, but eventually it will return to the pre-flare level. And this slide show you the coverage of the coverage of wavelengths of the Mauve. It's basically covered from 200 nanometer to 700 nanometer. And such wavelengths, I want to give it some example. And this is the first light measured by Mauve, released a while ago. And although the bottom line looks different from the top one observed by HST, I remember, but I was told it's after calibration it should be able to reproduce something at least similar to the top one. But at least from the bottom one, we can see the Mauve already shows some signature about H alpha, H gamma, H beta, H gamma, and H alpha. So and there are different lines. We can see the absorption signature, and all of those lines can be used potentially for the coronal dimming. And if the single wavelength is if the signature is not good enough, for example, in H alpha, we can integrate the wavelength by about 1000 A, so which should be able to increase the signature. But yeah, we can try what what we'll see. So the worst case, we can integrate over all the wavelengths to see if we can see any signature. And the observational strategy is so first we propose to observe three candidates. One is the ADLO, the second is EKDRA, and the third one is a little bit far further, but it's also more bright. So it's UXARI. Because the Mauve is currently still in the communication phase. So we will see. Ideally, we want to observe ADLO because it's much more active than the third one. But if ADLO cannot be observed because there's a very bright star beside ADLO, then we will switch to the other two targets. And the idea is we want to observe the star for 20 days and possibly with another 10 days. And every time we want to observe the star for about 6 hours, because each orbit will last for about 97 minutes, I think. So if we but it's unlikely we can observe the same star for the whole orbit. But we want to make sure each orbit will cover at least 30 or 60 minutes about the stellar observation. And then when we jump to the next, for example, if we observe 60 minutes for the first orbit, then we want to observe this again for the second orbit for another 60 minutes until we reach 6 hours. So such that we can possibly cover the complete phase of the stellar flare. And to see the possible UV dimming signature from Mauve. Yeah, I guess that's all. So thank you for your attention.
Thank you, Chuanfei. Does anybody have any questions? If you do, you can pop them in the Q&A box and Chuanfei can answer them.
Yeah, I think it's obvious. Just test some idea has been previously tested by other telescope, but the Mauve can give much longer observation for the same target. So possibly can, because I know, for example, this observation take a lot of effort by using telescope resource and take several years. I remember to collect the data. And the Mauve can probably achieve such goal with a short time scale.
Thank you. April, are there any questions?
Yes. So there are a couple of questions. I'm gonna read them out one by one. There's a question by Steve Kohler. How does the cadence affect things?
Wait, the cadence mean which parameter basically, like which cadence can he clarify which cadence?
I'm not sure. It's not there in the question. The question only reads, how does the cadence affect things?
Or maybe Stephen, oh, here we go. Gaps in the data caused by the orbit.
Oh, yeah. So because the stellar flare will usually last for on the order of several hours. Because sometimes we use test data, we can observe some stellar flare can last for at least actually for 10 hours. So ideally we want to observe the stellar flare continuously, so such that there will be no gap. So the answer is the shorter the better. but we also need to consider the exact the configuration of the orbital geometry. Yeah. So if it's too long, it's too long, then it's possible we will skip the the dimming phase. Yeah, for example, if you see here, ideally, if we can capture those segment during this curve, then we want to see the trend. But if the gap is too big, miss the whole dimming phase, then it's not good. Yeah. So the smaller the better, the larger the worse. But overall, we need to test how it look like maybe for the first few tests.
Okay, thank you. Another question by Yuta Notsu. Do you plan to investigate also flare UV continuum spectra?
Yes, but because this is when we measure those dimming, we need to integrate all the spectrum. So those continuous spectrum is automatically there, and yeah, I think if I cannot remember, but if policy allowed, it's open for collaboration about those data.
Okay, and one last question by Giovanni Bruno. What sort of systematics might we expect that could mimic dimmings?
Yeah. So for example, yeah. So this is the signature. For example, this is the coronal dimming on Proxima Centauri, and this system has multiple stars. For example, it's likely their result is correct. I did not want to say anything, but it's also possible because if we observe a system with multiple stars, then those star can also block each other in certain geometry, or configuration, so such that may produce some signal. But it's likely this paper is. I just want to say it's possible if we observe a system with multiple stars, and the configuration can also mimic something like that. Yes.
Okay, thank you, Chuanfei. There is one last question if you have a minute. It's from Huigen Liu asking, the detection would prefer the CME in the direction towards the observers or not?
The detection would prefer the CME in the. Yes, sure. Because for example, if we observe, either emission dimming, especially for the especially for the obscuration dimming, then it's much better if the CME toward us. For emission dimming, I guess it depends. As long as those regions, for example, show in black, the active region, and then because we will integrate the whole surface of the star, eventually equivalently, and then yeah. But ideally, if the CME toward us is better, in that case, we probably can also see some Doppler. We can also measure the Doppler shift more efficiently because there's no projection about Doppler velocity.
Okay, thank you. That's all.
Yeah, thank you.
Great, thank you. Thank you, Chuanfei, for that really interesting talk. So now I will hand over to Chris, who will do the second of our guest talks today.
Excellent. So thank you very much. So I'm going to talk about accretion variability of Herbig AEB stars, and my main collaborators in this are Kayvon Stassoon and Don Dixon from Vanderbilt University. So Herbig AEB stars are young, newly formed stars. In the general scheme of star formation, we have a dense core and a molecular cloud begins to collapse under its own gravitational pull, and because of its rotation, forms the central newly formed star surrounded by a disk. And there are bipolar outflows that are observed in this stage. As the time goes on and the cloud core either completely falls onto the central region or is blown away because of this outflow, you eventually wind up with just the star and the disk and the outflow. And then later on, presumably you're forming planets and you get a mature young stellar system, young planetary system. As it says here, this is for a T-Tauri star, but we think that much of the same thing happens for Herbig AEB stars. The Herbig AEB stars are generally thought to be the higher mass analogs to the classical T-Tauri stars. So if you look at a bunch of objects in the HR diagram, you've got log of the effective temperature on the x-axis and then log of the luminosity on the y-axis. And here you see in the black lines are mass tracks, pre-main sequence evolutionary mass tracks for different masses going from 0.5 up to about 4 solar masses. And what is shown here are a number of objects. You've got the lower mass T-Tauri stars on the right of the screen, and sort of to the left of this dashed line is where you would see the Herbig AEB stars. During this evolution, the internal structure of the stars is changing. So in the upper right here, marked FC, are fully convective objects. In the green, these are objects that have developed a radiative core. In the light blue, you have fully radiative objects. And in the sort of pinkish region, you have objects that have developed a convective core. And what is also shown in here are objects that have magnetic field measurements. So in the lower mass objects, objects that have been observed, if they have a red symbol or a blue symbol, they have a detected magnetic field. If they are black or this light blue, they have not had a detected magnetic field. And in the Herbig stars is shown basically between the red and sort of the gray. And what you can see here is while magnetic fields are detected very regularly for the lower mass objects, they are rarely detected for the higher mass objects, for the Herbig AEB stars. And we certainly think magnetic fields are very important for how accretion occurs onto the lower mass stars. So if in fact the higher mass objects don't have magnetic fields, things could be different. Just to show you that these objects do have circumstellar disks, this is an ALMA view of several different Herbig stars from Stapper et al. In 2019. So this is showing dust continuum emission. And you see a host of different geometries from very filled in sort of continuous disks to rings and gaps. So much of what very similar to what you see in the lower mass T-Tauri stars, you see an assortment of these things in the Herbig stars. In terms of what we think this disk looks like, at least as developed in the case of the lower mass stars, you have the broader disk that has both the dust and the gas. As you get close into the star, because of the stellar radiation, the disk gets hot enough that you expect all the dust to sublimate. So in the very inner regions, you would expect there to be perhaps just a gas disk. And then if the star does have a strong magnetic field, it is believed to truncate that disk such that material then accretes onto the star via these stellar magnetic fields. And for a more luminous object, so the Herbig stars in general are more luminous, you might expect this sublimation point to be further out in the disk so that you have that there's no question that the star should be interacting with just a gas disk. And then again, in the case of the T-Tauri stars, they have been studied very extensively. We have a well-developed picture summarized in a review article by Hartman et al. So again, the stellar field is believed to truncate the inner disk and redirect accreting material along the stellar magnetic field so that it falls onto the star near the poles. And when it does that, you are converting the kinetic energy of the infall into thermal energy and an accretion shock And I'll show you a little bit more details about what we think is happening there in a moment. And then there's also some sort of outflow. The exact nature of this outflow is still debated, whether it's something that's coming from very close to the interaction between the stellar field and the disk, or perhaps a component from further out in the disk, a true disk wind. And even some models have an accretion-powered stellar wind coming from the actual star itself. But what we do also see in the case of the T-Tauri stars is broad emission lines from these accretion funnel flows, so things like H alpha. And we see those same broad emission lines in many of the Herbig AEB stars. One of the reasons that people think that the same models for the low mass stars are happening for the higher mass stars. Now, that previous slide showed the idealized case of an aligned stellar dipole. Almost certainly, the magnetic fields are not pure dipoles, and they're not purely aligned with the rotation axis. And in those cases, you tend to see the magnetic fields directing the material onto smaller regions of the star at the foot points of some of the magnetic fields. So as the star rotates, you would expect then a rotational modulation of accretion-related emission. So we mentioned that the Herbig AEB stars maybe have weaker fields, maybe don't have magnetic fields at all. And so if the magnetic field strength gets smaller, you would expect the gas disk to extend even closer to the star, perhaps going all the way to the stellar surface, forming a boundary layer where the disk material is butted up against the star. It's not quite clearly shown in this cartoon diagram, but you would also expect if you move the disk in closer to the star, even if it is truncated by a stellar magnetic field, the regions on the star where the accretion should occur should be closer and closer to the equatorial region, and then ultimately right at the equatorial region if you're in the boundary layer situation. So in terms of if there is this accretion shock, this accretion flow, what we think is happening for the young stars is you have infalling material coming in at free fall velocity, free fall depending the exact velocity depending on where it falls in from, so how close the inner edge of the disk is to the star. It heats up in a shock, heats up to 1,000,000 degrees or so. It's optically thin at that point, and as it settles onto the photosphere, it slows and cools, eventually going through 100,000 degrees, 10,000 degrees, getting down to the temperature of the actual photosphere. And it becomes optically thick at around 10,000 degrees, and so this accretion continuum shows up as a Balmer jump, at least for the low mass stars. So you add this accretion emission to what you would expect for a naked stellar photosphere, and you get the spectrum of a young star, which has these strong emission lines and this bright continuum at short wavelengths, which Mauve is ideally suited to observe. If the disk comes all the way down to the star, though, you would be forming a boundary layer. And what is key then is what is the difference in the rotational velocity between the star and the disk, where the disk is trying to come down to the star, because that difference in rotational velocity, you're taking that kinetic energy and heating up the material. And one thing that we do know about the Herbig stars is they are generally rotating much more rapidly than the T-Tauri stars. And so we might expect the character of the accretion emission to be different in that case if it's in a boundary layer. So in the interest of time, I will skip with this, just in terms of what some of the information or some of the evidence that we have smaller magnetospheres in the Herbig stars. If you look at the helium-10-830 line in a sample of T-Tauri stars, shown here in red from Quan et al., or if you look at them for a sample of Herbig AUB stars, in both objects you see these red-shifted absorption features, these inverse P Cygni profiles in many objects. And if you just measure the velocity of those absorption features and compare that to the escape velocity of the object, what you see is if the velocity of that redshifted absorption was equal to the escape velocity, you would be on this upper dash line showing free fall from basically infinity. And as you go down to these other dash lines, this is indicating free fall from a radius that is 1.1 times the stellar radius, 2 times the stellar radius, 4, 8, and so forth. And so you see that the T-Story stars, the lower mass objects, tend to cluster around these lines where you are seeing free fall from a larger radius than you see for the Herbig stars. So that's one indication that you might have the disk truncation radii be smaller in the Herbig stars. And again, as we pointed out in this diagram, because of the paucity of magnetic field measurements in the Herbig stars, that kind of all fits together. So what might Mauve see? Well, one of the issues, I mentioned that the optical, where that accretion continuum reaches optical depth unity, has a temperature of about 10,000 degrees. You know, that's roughly the temperature of an A0 star. And so there has been concern that maybe you couldn't see the accretion continuum in a Herbig star because it has roughly the same temperature as the photosphere. But because the photosphere of an A-type star has a Balmer decrement, so you have flux, much lower flux on the blue side of the Balmer jump than compared to the red side. Even a 10,000 degree black body should much more dramatically affect the blue side of the Balmer jump compared to the red side, and you could hope to measure that relative increase in emission on the blue side relative to the red side. So we can take this basic idea and model maybe what Mauve will see if we use the star AB Auriga, which is an A0 star, magnitude of 7, and do it in a quiescent phase, so basically no accretion shown in the sort of yellowish orange, and add an accretion excess that is 40% of the total luminosity, kind of based on that previous model from Fairlamb. You would expect a somewhat of an increase on the red side, but a larger increase on the blue side. And this is what those spectra would look like after 300 seconds of exposure with Mauve. And so you can begin to look for these changes in the spectra, particularly as you look for variability, because we do know that accretion variability is very regular in the T-Tauri stars, and so it is also expected in the Herbig star. And in fact, here is another Herbig star where you have two simulated Mauve spectra, again, a 300-second exposure. And these spectra, these model spectra that were inputted, are based on actual X-shooter observations that showed a dramatic increase in the flux for this Herbig star from one epoch to another. And so we hope to then study this accretion variability in the Herbig stars. We can also look at the H-alpha line, as was mentioned in the previous talk. We know that the luminosity of H-alpha is correlated with the accretion luminosity for the lower mass stars. As was mentioned, Mauve is going to be a low resolution mission, but the H-alpha line in these Herbig stars can be quite strong, and even once you convolve with the Mauve spectral response function, you should be able to identify the H-alpha line and study its variability. So we, in the first year, have identified a number of Herbig stars where we will basically be getting daily, not exactly 24 hours, but daily observations over the course of approximately 80 days. And then for the stars shown in the red here, we will be getting additional observations beyond the original 80 sort of every 4 days, so that we can begin to study sort of longer time period variability. And the goal is ultimately, Mauve is a 3-year mission to observe these 6 stars highlighted in red over the entire 3-year mission to cover quite a range of variability for these objects to see how we can distinguish the variability of Herbig stars from their lower mass counterparts and explore what that is telling us about the geometry of accretion in these higher mass objects. So in the interest of time, I will stop there, and if there are any questions, I'll be happy to try and answer them.
Okay, Chris. Well, thank you so much for that really interesting talk, and thanks also to Tuan Fei for the talk. We'll likely repeat with many of our other members as we move throughout the year and show the many use cases that Mauve will support. But thank you so much for those really interesting talks. I will share my screen again, and I'm going to hand over now to Ariana, who will give us a brief update on commissioning and first light.
Thank you so much, Richard. So yes, after having undergone a successful launch and early orbit phase, Mauve is now currently in its commissioning period. So we can confirm that all hardware is performing well. The solar panels have been deployed successfully, and all systems are on and working nominally. A detailed platform commissioning is currently underway, and the initial payload commissioning has been successfully completed. We've also acquired several stellar spectra with observations that are spanning various spectral types and magnitudes, so from O, B stars all the way to M stars. Next, please. Thank you. So last month, we announced Mauve First Light in a press release. And for first light, we chose to observe Eta Uma, a bright B3 main sequence star whose flux peaks in the UV wavelengths. So this is a perfect target to start calibrating the Mauve instrument. So here in pink, you see the spectrum of Eta Uma acquired in a single capture by Mauve on the 9th of February with a 5-second integration time. And in blue is the Hubble Space Telescope's TISS spectra of the same star recorded by 3 different grisms. So the Hubble spectra shows calibrated data at high spectral resolution, while the Mauve spectrum shows raw data in count units. The spectral features of the Mauve spectrum are different from the features on the Hubble spectrum because the data that has been delivered by Mauve is the result of the matrix product between the true stellar spectrum and the instrument response function. And we can also confirm that the Mauve observation of Eta Uma is in very good agreement with the expected signal that we obtained from pre-flight simulations. So this is another confirmation that the systems are working as expected. And in the next webinar, we'll be delving into the details of how we've been calibrating the Mauve instrumentation and also how to approach the analysis and interpretation of Mauve data. And with this, I'll hand over back to Richard.
Yeah, thanks, Ariana. So launch was obviously the first big milestone for the mission, but first light was a really important milestone. Proves we've captured our first spectra and the majority or all the systems are working as we planned. So thank you, Ariana. I'll hand over now to Ben, who's going to introduce how we're delivering the science program.
Thank you very much, Richard. So as Richard said, my name is Benjamin Wilcock. I'm the Senior Science Program Manager here at Blue Sky Space, and my role really is to help coordinate all the planning activities that the members undertake. So as you can see, we're working with 10 different institutions from around the world right now, and you can see their logos along the bottom of the screen there. It's about 20 researchers that we're currently collaborating with. And the people that have joined the survey so far are planning for year 1, because on Mauve we do year-to-year planning for the science themes. And right now we're trying to understand which science cases are of interest to the member community, how we optimize that across an entire year. So we're going through a series of different planning phases and stages. We've actually just released our first publication on the 10 science themes that have been selected for year 1. Year 2 will have different science themes, and as you've seen from some of the presentations this morning, some of those will be carried into years 2 and years 3, and it's likely we'll have new members joining throughout year 1 and year 2, so there'll be additional science cases that get added in. If you're interested in learning more about the detailed plans for those different science cases, I would look at the paper, which is on arXiv currently, and you can link to that with a QR code. But really, I guess the most important thing for us to convey is that it's not Blue Sky Space that are deciding the science cases, that are deciding the target lists or the observational strategy. It's actually those members that are joining onto our program that decide what gets done in any given year on a Mauve survey program. And as I said, we've kind of selected 10 core science themes, and those can be broadly categorized into 4 core areas. And you can call those stellar variability and activity, exoplanet hosts, hot stars, and then exotic stellar binaries. So today you've listened to 2 presentations, one from the stellar variability, one from the hot stars. But actually, if you go back to one of our previous presentations, we've presented on a couple of the other science cases, and our plan is to provide our members with a platform to convey those science cases. But Mauve ultimately will be undertaking a series of different observation programs. So, for example, looking at the exoplanet hosts, we'll be trying to understand the flaring activity across stellar life cycles, but also maybe doing some observations of HWO targets ahead of that launch to help optimize target selection. But in addition to that, we'll be doing things like exotic binaries, where we're looking at the evolutionary pathways for multi-star systems. So across the 10 different science cases we have quite a diverse range of targets that we'll be studying. And we wanted to give you a kind of a glimpse at the target list and the distribution of those targets across the sky. So what you can see is Mauve's original field of regard plot here. And actually, I should note that during the course of the commissioning phase, we've actually been able to release some of the constraints that we originally placed on the field of regard, because if you look to the -45 and +30 declination, you'll see dark blue coloring, which originally meant no observability. Actually, during the course of commissioning, we've been able to release some of the constraints, which means we could see up to 90 degrees declination. So this target list is likely to increase, but as you can see on the left-hand side here, we'll be studying O-type stars all the way through to M-type stars, predominantly with a focus on the brighter stars, as Mauve is a low resolution, 13 centimeter telescope. It's optimized for brighter targets. But what's important here is to note that many of these targets are actually observable for hundreds of hours. And actually, because we've released some of the constraints, we can see them for multiple months now. So we'll be able to see different sections of the sky for several months at any given time. So 287 candidates that have been selected so far. As I say, because we're still in the commissioning phase, we're still doing the survey planning and optimization. So once we know some of the final constraints from the commissioning activities, we'll be able to finalize the exact target list that gets implemented. But as Richard said earlier on, 5,000 hours have been allocated already to the survey science cases that we've received, and it's likely that we will increase those number of hours as we receive new additional science cases to input. But all of this data ultimately ends up on our StarDrive platform. So our goal with Blue Sky Space is to provide a set of tools and observations and a planning strategy that is easy to use for all members to access. So we built this custom platform called StarDrive. It's where all of the data will be housed, but also you can access all of the simulation tools. So for anyone who's interested in accessing the payload simulator to understand what Mauve can do for different science cases, you can request access from Richard or Parul, who will be able to provide you with a link to access a public version of this payload simulator, which has over 400 STIS spectra that you can run through. If you'd like to see a bespoke simulation as well, they can also provide that to you. Other than that, our hope is that we'll be able to present in the coming weeks and months a series of updates based on commissioning activities. But our goal over the next kind of few months internally is to start doing some observations and preparing a publication to use real observational data to demonstrate for the science cases we've identified in that first publication, what's the performance and what's expected to be done over the remaining year once we get into the full survey, the full survey cycle. And with that, I'm going to hand back over to Richard.
Great. Thank you, Ben. So I'm aware of the time. We're approaching the hour. So a few quick notes, closing notes from me. Firstly, as I mentioned in the last webinar, we've talked about year one as part of this session, but we have another year to plan. So a new science team is formed. Some members from the old science team will be parts of that. And science planning will start in May 2026 for year two of the program. And those operations will begin in June 2027. So you can be involved in that, and it's a really great opportunity to become part of the science planning team, bring your ideas and how you'd like to use the telescope and help shape and design the observational program. We typically hold virtual science team meetings, probably monthly, maybe every 6 weeks initially, and they will increase in frequency as we move towards the start of the year. And then we also have in-person meetings. So that's a great opportunity to network and meet with other members of the collaboration and talk about the science and your research. All the activities are managed by Ben and the team using the StarDrive portal that we introduced earlier. For year two, our members may decide to extend some of the themes from year one, or they may decide to completely focus on new themes and ideas. All ideas are welcome. For year one, you can actually still join year one. Take a look at the science themes in the paper that Ben alluded to. You can join, you can use the data, you can collaborate with any of the existing science theme members. There are 10 science themes, 5,000 hours, as Ben said, 287 targets have been requested. One note, as we fully characterize the kind of true in-orbit performance and all the overheads associated with moving the satellite, slewing, settling the satellite, we will possibly release additional hours. And those hours could be used to extend existing themes or add new ones. I'm sure the eagle-eyed of you have noticed that 5,000 doesn't add up to all the hours in the year. What's that? Well over 8,000 hours. So watch this space because we may release additional hours as we move forward into the first year of science operations. If you do want to take part in the program, please contact me, Richard at bssl.space, and I'd be glad to set up a call and talk to you about the process and how you can participate. Final note, Ben's talked about the payload simulator. Here's the QR code. If you scan that now or when you're watching the video back, when I send you the link, you can gain access to that. It'll make a request to the payload simulator, and you can see if Mauve can potentially address the science you want to do. If you're not sure about the tool, we can also do some custom simulations for you if there's anything a little bespoke or complex that's needed to be done outside of the tool. Okay, feel free to send us any questions or any questions to me on richard at bssl.space. That leads me nicely onto the next webinar that Ariana mentioned. So when we have moved through the entire calibration process, we will have a much better understanding of the true performance of Mauve. And we will have a webinar dedicated to that, which Ariana is likely to lead. And we're likely to do that probably end of April towards early May. So all that's left to do is to thank all the speakers today. Thank you, Chris, and thank you, Chuan Fei, for being our guest speakers. And I look forward to seeing you at the next webinar. So have a great weekend, everybody.